about, we're going to look at work, power, and energy here. How we calculate work, power, and energy. Okay, so now if you look at, there's a few equations in our book here, or in your Wiley Plus. If you see here, we've got work is force times distance, force over distance, all right? And then we'll turn a couple pages, and here on page 55, table 3.1, this is a good table, and you should really study it to where you understand it and see all the different relationships with it. What I like to do with this table is think about the units and deconstruct them a little bit so I understand the units. So from last time, we have force is equal to mass times acceleration, and we learned that force is measured in newtons, okay? And work is force times distance, and these are measured in, among other things, a quantity called a joule. So joule, as we learned in the lecture, was a guy who helped show that energy was interconvertible. In his case, he showed that kinetic energy could be converted to thermal energy. So we have a unit of work named after him. And interestingly, energy is, if we look here, the ability to do work. So energy is also measured in joules. We'll see that energy can be measured in other ways as well. Okay, and then power, here's an interesting one. This is work divided by time. Work divided by time. Okay, so this one, or it can also be energy divided by time. Energy divided by time. So this one is measured in this thing we call watts, named after James Watt, who did the steam engine. We talked about the horsepower. There's some stuff in the book about that. Okay, so let's look a little bit at this. Look at work. So work is force over distance, and force is measured in newtons. Okay, so work is measured in Newton meters. All right, so a joule is a newton times a meter. And if you remember what a newton was, a newton is a kilogram meter per second squared. And then we multiply that times a meter because it's a newton meter. So a joule is really a kilogram meter squared per second squared. All right. Now, if we divide joules by time, we will actually get a kilogram meter squared per second cubed. All right, and so that will be similar. That's the breakdown of a watt. Okay. Okay, so let's look a little bit first at some problems. Your book points out that, for example, you know, something like a stereo system will use 250 watts. Okay, you could look on the back, for example, your computer, stereo system, television, a small one would use this power. You would find this on the back of some device. You know, I don't know. This calculator doesn't have one, but so the book asks you if you ran it for 3 hours, all right, what you would get is this 750 watt hours. And we'll see how these watt hours work later when we do electricity. But a lot of times your energy bill or even your battery, interestingly, will come in units of watt hours. Maybe your battery will be milliwatt hours and your energy bill may be kilowatt hours. So we'll see this is sort of an integrated way of looking at power. And so you get power times time. If you power, since it's energy divided by time, we multiply it by time, you get energy. So power times time is energy. All right, so then the next one we have also in this chapter is the KE, or kinetic energy, is equal to 1/2 mv squared. All right, so we talked a lot about things flying around, arrows or water or wind. This kinetic energy, when you throw a baseball, we can actually calculate it, and we'll see we can calculate it in terms of joules. All right, so an object with a given mass flying at a certain speed will give us a joule, or an estimate of energy. All right, so the book gives us this example of something with a mass of 4 kg, and it's traveling, the velocity is 10 meters per second. All right, so to set it up, our unknown is our KE, and we're going to just say 1/2 times 4 kg times v squared. That's 10 meters per second squared. All right, and hey, look at that. We're going to have kilogram meter squared per second squared in our answer. So let's see, 1/2 times 4 is 2. 2 times 100 is going to be 200 kg meters squared per second squared. That's our kinetic energy, and we know a kilogram meters per second squared, when you come up here, is a joule, or a Newton meter. So this is going to be 200 joules. All right, so an object flying through space will actually have this energetic property of 200 joules. Okay, so just something interesting, like when you go to another country, a lot of times you'll find that the food is given to you, the estimate of the food is not given to you in calories, it's given to you in joules, or kj, kilojoules, kj, like that. And there's the metric system for you. This would be equal to 0.2 kj, okay? But there's a metric system for you, and they use this estimate of energy, and it's really the same as a calorie. A calorie is basically chemical energy. A lot of times the calories in our food are chemical energy, and so joules can also be a form of chemical energy. All right. So looking at your book, or your lab exercise for this week, this would be lab 5. Let me start a new piece of paper here. It asks you, there's one question on here that asks you about a 1 kilogram mass, and that's going to be your mass, and it asks you how much to elevate this 1 kilogram mass for 1 meter. How much work is necessary? All right, so this is super easy. Work is just equal to force times distance, and so you gotta and force is equal to mass times acceleration. All right, so you need to the force you need is going to be equal to mass times, it's really going to be equal to g, like we talked about it. So 1 kilogram times 9.8 meters per second, we're going to need 9.8 newtons to lift this mass of 1 kg by that's the force we're going to need, is 9.8 newtons, and then we just multiply this times 1 meter. All right, so the work is going to equal 9.8 times 1, 9.8 Newton meters, or 9.8 joules. Don't forget, kilogram meters per second squared is in Newton. Force is measured in newtons, okay? So then it says if a weight is dropped from this one meter height, all right, let's say this is 1 meter, and here it is at 1 meter, and it's 1 kg. It's now setting up here in having potential energy, and how much, first it asks, how much time will it take for it to fall? Now we're assuming we're on Earth and so on. Okay, so now we're going to use the acceleration of gravity, and we're going to use this distance, and we're going to use this equation from last chapter is distance equals 1/2 AT squared. All right, how long we want to know for setting up this 1 meter height and an acceleration of gravity, how long will it take to fall? And using the conversion we did last time, we know that T is equal to 2D divided by A. All right, this is just doing this equation, isolating for T. Okay, so now our D is 1 meter, our acceleration is 9.8 meters per second squared, and we multiply that times 2, so it's really 2 divided by 9.8, 2 divided by 9.8, and I'm going to need my other calculator to do a square root. All right. All right, so here we have, let me get rid of this. So then 2 divided by 9.8 is equal to 0.2. All right, and then I want to take the square root of that. All right, so my T is going to equal 0.45 seconds about, okay? This is distance in meters. A is meters per second squared. Cross these out. And then you just have the second squared and you take the square root of that. And by the way, don't forget, in this case, A is 9.8 meters per second squared. This is just a gravity on Earth, or G. All right. Okay, so